Okay, this is my solution to problem B3 of William Putnam competition problem 2013. So first, let's read the question. So P is a non-empty collection of subset 1 through n such that these, if S and S prime is coming from the collection, is closed under intersection here and the union. The second condition here is saying that if you have a collection of a set in the collection, not empty, then you can find another set underneath it. The subset has one fewer elements. What this guarantees is that if you have a k element subset, it guarantees that there is a subset with k minus 1 element, and this applied it again to k minus 2 elements and so on until you get to one element and go down to the empty set. I realize that explaining this part is unnecessary, so I'm going to skip that part. And next part is about this condition. So the function is given on that subset inside this collection, so real value is assigned, empty set goes to 0, and it satisfies this type of functional equation. A good example of this function is a number of elements. So f actually measures a number of elements. So f of this union is number of elements inside the union. Of course, is number of elements in S and number of elements in S prime minus the overlapping part overcounted, subtracted off. It's called exclusion and inclusion principle. So that's an example of this type of function, but it is asserting that must there exist real numbers f1 through fn such that that function value coming from this given function actually is equal to this sum. Here's I is going through that subset and they're adding up the assigned values. Of course, there's a fixed n values, and as we vary s, and there's this fixed value that does this thing. What I'm about to show is that if we happen to have that property, or if the function is even defined in this way, I'm going to show that this implies this functional equation, just using the example. So for example like this, suppose we have 5 elements, 1 through 5, and we have the functions given. Not given, the function is actually defined in this way, then I'm going to show that it implies this functional equation. So we have this 5 value assigned, some well-known 5 real numbers I chose. Then this function is defined like this: f of 1, 3, 5 is values of f of 1, f subscript 1, excuse me, so that's going to be pi, and f3 is inside that set, so we're going to use f3 there, and f3 there, so we're adding e. 5 is f5 is ln2. So that's the meaning of this whole thing. So there is this predetermined n values such that function values of this subset is calculated like this. So if we have that, and this functional equation follows nicely. So here's an example. If I have two sets like this, 1, 3, 5 and 2, 3, 4, where this one element overlap, here's 3 and 3. So I'm going to calculate this inside. First, of course, is 1, 2, 3, 4, 5, the entire thing. According to that definition, it's going to be this: f subscript 1 all the way up to f5. That's the sum of all that number. And I'm going to compute the right-hand side, which is like this: f135, and that's this term. So all these elements in that set serves as an index. And the second set as prime here is 2, 3, 4. So f2, f3, f4 is the element. So we have these two things. You can see f1 through 5, f2, 3, 4, and we're adding these two things. You can see f3 and f3 repeats. So that's exactly coming from the intersection of these two things. So if you subtract off f3, after you add these two things, you arrive at exactly to that form. So although I'm not proving, which is not what is asked to prove here, that if we have this definition, it follows easily. Of course, what we have here is not those. We have actually this functional equation condition, and we're asked to show that is it true that there's this n value such that this thing holds. First, I started with believing that it seems like a sufficient condition, so I believe there are values, and later when I actually try to prove it, I realized that there is this weird construction that it seems like I can construct a counterexample. Then as I throw in more and more property that was imposed in the problem, I realized that it's actually true. So that's the experience I had with this problem. Right, here's the beginning of the proof, but I'm going to assume all that the entire set 1 through n is actually inside the collection. So this is typical, assumption without loss of generalization kind of stuff. So what I'm calculating here, I'm collecting all the subsets in the collection and taking the union. That's what this is about. And suppose that had m elements in it, and I'm going to relabel it like 1 through m, and everything else is accordingly relabeled. But if m is less than n, then you can see all the elements you see is happening inside this collection is really 1 through m, and remaining part from m plus 1 to n is not occurring at all, then actually you can use that as a 1 through m and don't bother with the rest of the problem. So you can kind of reduce the original setting through 1 through m and not bother with other part. So I hope this assumption is okay. So the next part, assuming that 1 through n is all in that collection, what we're gonna do, we're gonna start with the full set 1 through n is in the collection. Remember, there was one condition that allows us to find a subset with one fewer element and so on all the way down to empty set. So that's in general written like this, and I wrote it here as an example. So I'm going to check if it's really tight. So I squeeze in a little bit. So here we are. So that's what we have. It is something we have given size n, but it's not unique, and our construction kind of depends on our choice of this chain. So I try to be actually very sensitive in my answers. My dependence on my choice of this chain. And I like to claim that once you have this chain, and it's going to completely determine the value we're looking for, fj's, if they work, and let me explain what I mean by that. This will completely determine these values fj, and we hope that the function value f at that set is always obtained with these values in there. So whether they work or not, this chain completely determines this value fj. So first I'm going to give you a straightforward definition of how they're determined. I'm going to explain a little bit. So this has one element, not necessarily one is in there, but it has one element, it has two elements, all the way up to it has 5 elements there. But you can relabel it again so that M1 has 1, M2 has 1 and 2, M3 has 1, 2, 3, and so on. So I can assume that Mk in this chain has 1 through k. With that clarification or simplification, I'm going to define those fj value in the following way. F1 is going to be the function value at fm1. F2 is going to be the difference of these two function value, fm2, fm1. F3 is going to be the difference of these two function value, and so on. F5, f of m5 and f of m4 will be f5 in this example. So here's a picture. So with this 5 examples here, this little one here is m1. This one with it 1 and 2 is m2, and this one is m5. So that first set m1 has 1 in there, so that has a function value f of m1, and we're going to of course make that as f1, this function value, because that's the element inside that set. Now we have this m2, 1 and 2 in there. It has this function value fm2, and we want to make these two things equal. We want to figure out the function value f2 such that these two things are equal to each other. We already determined this f1 value, so f2 must be fm2 minus f1, which is also f of m1. So we have 3 elements in here, and that's the function value, and this is what we hope to these two things to be equal to each other. then f1 plus f2 is now has name f of m2. If these two things are equal to each other, f3 must be fm3 minus this quantity, which is also known as f of m2. So that's what you're seeing actually here. So that's the motivation of this this thing. I did not state, well, I'll eventually state that important part that I was sloppy and didn't include at the end, but I hope I'll catch it later. So this is, after all discussion, this is, kind of concise statement. We define this fj like this. There's nothing ambiguous or undetermined like this. Is fj are completely determined like this. I'd like to separate this function f, this idea from that function f. F is already given, so I define it again. gs is going to be defined like this. You collect all the elements in there and add up this function, this fj value that is occurring, this index whose index is occurring inside this s there. Think about that pi e and ln2 example that I showed. So we have this definition. We want to show every s value, these two function values, equal to each other. So that's kind of reformulation of the problem, and it is depending on this choice of a chain in here. So it's slightly more specific than what was asked to prove. So here again, I think I said it already, this I have no idea about this uniqueness of this chain, but once you have this chain, this value is uniquely determined depending on mk's. Next part is, I'm not proving this part, but I hope you find this intuitively true, that if not so, then and you have to think about that very first example I listed with 5 elements with a pi and e and 1 assigned. So if g is defined like this, is sum of this value whose index is coming from that input set s, then it naturally satisfies that functional equation, that inclusion and exclusion principle function there. So this will go through all the values, index coming from s and t, and this one index coming from s and index coming from t, and that's, f values, fj values, and subtracting off this overcounted here. So I hope this is intuitive. So I'm not proving it here. But one thing I'd like to also point it out before we move on is this part in here. Fk value I constructed here, and I do not know if it is independent of this choice, choice of my chain mk here or not. But with that choice, I have this one determined. So I'm gonna bring this choice in everywhere, and when I approve it, I have to be sensitive with that choice. So here's the kind of reformulation of the problem. So P is a collection is given, and the function is given, satisfying that inclusion-exclusion principle. And the choice of chain, we choose it, that's possible because of one of the property. Then I was saying that there's a unique set of values fk, like that, and we define g. Once you define g like that, we want to show that our function value of g is actually exactly the same as a function value of f. So only difference in here, I separated, I defined this new function, and then it's depending on the choice of the chain. So that's slight more detailed version from the original problem. I originally had long solutions, and then it occurred that while I'm writing that solution, occurred that actually the induction works. So that with that induction, the lengthy argument that I originally proud of was reduced really quickly. So here's how the important part. When you do the induction, you always use the induction hypothesis from the lower case. So process of pulling out the lower case from it, I'm going to call it a reduction. So that's what we are about to do. So in this example, the whole thing has 5 elements in there, and F5 is a tree of subsets, and then we're looking at it here. So if I choose a subset in that collection T and collect all the subsets that is contained in that T, so in that tree we have these type of thing described in here. So we can certainly think about this collection. I'm going to denote that collection by P bar. And then key thing is that this new collection, made out of possibly necessarily constructed out of fewer elements than 1 through n, actually satisfy the property of the collection we're considering. Closed under union and intersection is that if you have two sets underneath that T, of course it's going to stay within the two. Union and intersection is all contained with that T. And I summarize the second condition as the existence of this chain, that if I have one element as a subset in here, then I should be able to find one fewer element down there and one fewer element down there, which is actually happening in this bigger collection, and it's kind of downward is very friendly to the way I constructed this new sub-collection P bar. So we have a new collection with the fewer elements. That's where this induction kick in to the fewer elements. Is really powerful if you think about this type of an induction, that you think that it is not the place to apply the induction. Is just statement is too broad and huge, and but it actually works if you think about it. It's only understood and you believe because you went through non-induction proof, and from that detailed version, and you know that induction is going to work. So if you're just looking at this induction version, I understand that it might not be easy to believe it's an actual proof. One other thing that I'd like to introduce before we move on is that if the function f is given to this entire tree, then we can reduce to the smaller tree in here. Of course, all this thing is still contained in the collection B, so we can simply restrict that original function down to a smaller collection. Then I'm going to call that f bar. So of course induction begins with the base case, n being 1. So if there's only one element involved, and there are two sets that are only possible, this empty set and singleton set. So we have to show, in this case, g of s is equal to f of s. If s is an empty set, this is assigned to be 0, and if you look at the definition, if s is empty, this null sum is a conventional to define that null sum being 0, so that 0 equal to 0. But only other possibility that we consider is this only other possibility, m1. So s being m1, it contains only one element, 1, so that's going to be f1, and that is how it's defined here. Therefore, it's the same as fs. So that's our base case. So heading to that real part of the induction, let's clarify the induction hypothesis here. That statement is true whenever we're dealing with the original set length less than or equal to n. Actually, this version of induction is not necessary, so you can just assume the statement is true for all n. Then we're going to look at n plus 1 elements over here. So here's the beginning of the induction part. Now we have a collection with subsets of n plus 1 numbers, and f is a function on P satisfying the functional equation, and this is a chain we choose, okay, from this 1 through n plus n, and this chain has n plus 1 element here, mn contains some n elements, and so on. They all satisfy the conditions given. Now G is not given, just determined by our choice of this chain and this function f. So G is uniquely determined by the chain we chose. So what's the next step? Is reduction in induction. So what I'm going to choose is this mn, is one right below. This mn plus 1 contains everything, and mn is missing only one element. That's the relationship between these two sets. So consider P bar, the smaller one, smaller subcollection underneath mn. So here's mn, and that's denoted by P bar. Now f can be restricted down to this subcollection, so we have that f bar. So that kind of goes into, we have a new collection P bar, and we have a new function given an f bar. It's not really new, it's a restriction, and it's a subcollection. Now, when you apply the induction hypothesis, we have to make this choice of the chain. To compare this nicely with the original one, we have to compare that with this G bar. G bar here is kind of given for this smaller subcollection, not determined. So we have to think about which subchain we're going to use for this smaller subcollection. Right thing to use is that originally we have this chain 0 to n plus 1, and we're choosing the subchain in here, and that's our choice of a chain. So with that collection, we have G tilde, maybe, not G bar, is determined by this subchain. If you think about how G is defined, and it is, working the way up from an empty set and throw in one element there and throw in one element there. So G is constructed by looking at this entire chain, and G bar is just looking at that much of the shorter chain. So I'd like to claim that the function G bar actually agrees all the way up to M4, obviously. So the function G tilde, that is determined by this choice of subchain for the shorter length in this statement, actually agrees with the restriction, a G bar, that we're inheriting from the upper level case. So G bar is a function uniquely determined in the chain. It's not the definition that I'm claiming here they agree, because the way the G is defined, namely working the way up. So here I'm just creating some rooms. So I collected the condition that I wanted to use, and G's for that m plus 1 level, and these are the reduction, subcollection, and restriction, and G bar is a restriction, but it is the function determined by the subchain. Next part is using the induction hypothesis. We're going to choose that our goal is showing that Fs is equal to Gs. So I'm choosing that set S inside this Mn underneath this tree. Then we can use induction hypothesis. So F bar and G bar is the same value, and because of the induction hypothesis, when S is coming from that subcollection we're looking at. But this is a restriction, so it must be the same in the original function as well. So that's done. That's actually the magical part, that everything is shoved into this induction hypothesis, and we have to deal with a very simple case. So next thing is that, of course, what if we choose a set that is not inside this, underneath this Mn tree, then it's denoted like this. The key thing is the following. Mn contains n elements. Mn plus 1 contains everything. Mn is missing one element, and T is not under this Mn. Therefore, T must have that one missing element that M does not have. If it has that element, then it's going to be underneath this tree, because it has n elements or fewer. The point is that this T must have that elements that Mn is missing. And therefore, if you take the union, you get the entire thing back, Mn plus 1. Maybe you have to write down some of the examples of this situation, but it is true, because Mn missing one element and T not being contained in Mn implies that this union of these two things will get everything. So that's the important key observation, and here's what we have. T and Mn, the union, it becomes the whole thing, and S is the intersection. Then it is, of course, a subset of Mn, because it's intersection, and this whole thing is still in the collection, the P that we originally started with, the n plus 1 element. Therefore, S is under this tree. So we have T outside the tree and S underneath the tree. So these 4 elements here, Mn plus 1, T, Mn, and S, are kind of little building block that I use to complete this problem before I think about using this induction. So I'm going to show you briefly that these are some of the things that I went through, changing my answer from yes to no to yes, and playing with this various detouring block that kind of resembles what I just did. And eventually I realized it by looking at this type of tower that, this, if you if you're close to the top tower, I realized it determines actually everything way back down, and that triggered me that induction might be the right way. So here that is this statement about union and intersection, and I'm applying the function there. So this whole thing is mn plus 1. This is actually union, so you can split it like this and subtract off this part. That's the functional equation. And I'm going to apply, write down the same statement about the g that we're comparing. The mn plus 1 is again the union. Now this one naturally does have that inclusion-exclusion principle, so we have that. Think about these last two terms. They, because of the induction hypothesis, they are all under an mn. So fs is equal to gs, that because s isn't here. mn and gn, mn's of course in this set, so they're all equal to each other. And difficult at this point, the part that is maybe not easy to see is why is these two things the same, because this guy's an outside, and I'm claiming that it's natural because of the way the gm plus n and gmk are defined, because when we define this g value, we're just throwing in the one value at a time such that this thing holds at least for this type of sets that are appearing in our choice of chain. But I'm going to go back to the definition of G and kind of convince you, help you to understand why these two things are true, the same, equal to each other. Right. Roughly this is where it's defined. So for example, G of I'm claiming that if S is one of those MK, and these two values are equal to each other. That doesn't use any induction or anything. It's just a pure definite, simply the way G is defined. So I'm going to start from here. I think that's one example will convince you that it's true. M3, I wanted to show f of M3 is equal to G of M3. That's what I want to show. What is G of M3 here? M3 has this element 1 and 2 and 3. So it's 1 and 2 and 3. And you're adding F1, F2, and F3. That's what this G of M3 is, sum of F1, F2, and F3. Now this is how it's defined. When we add F1 and F2, you can see FM1 and FM1 cancel. When you add this F3 to that, you can see F2, FM2, and FM2 cancel. So only FM3 survives. So that's straightforward definition, proof from the definition. But if you think about the principle of determining this value, that's also quite natural to believe that G is constructed such that these two values are equal to each other, at least for this chain. So that's why this guy is equal to each other. Again, not from induction, is from the definition of Gn plus 1. So every other terms are equal to each other, so we had no choice. This Ft must be equal to the Gt as well. So that's the proof. Let me summarize it here. We first chose S and showed that an Fs equals Gs because of the induction hypothesis. Everything is happening here is assumed. And T, when T is outside this tree Mn, then we just show that it still have to equal to the Gt. So this was the original problem. The only thing that I added here is specifically the choice of the chain that I play with, and I separated these two notion, which is the right thing to do. So that's my solution. Thank you.